So let the fun begins. Now we're going to create our Pathfinder. Okay, let's create a new list. Now let's create Pathfinder scheduler, which we're going to call Pathfinder master. Let's open that. And the actual Pathfinder. The scheduler will come later. For now, we're just going to do the Pathfinder. Okay, that's going to take a significant amount of time to do as well. So let's first open that up. Okay, let me see my notes. Now, perfect. So let's delete that, Let's add namespace. First of all, what is a Pathfinder? Pathfinder basically creates you a path onto a grid that you go from one node to another node. Okay, so with that said, we're going to create a constructor for this, because once there is a job or a schedule pathfinding task, you can't really change, and you don't want to change the variables that you used to do the pathfinding. Okay, it's not really as frightening as it sounds. It's pretty simple. So let's do first of all, we're going to need a callback that says our pathfinding is complete. Okay, and that is going to be returning us a node path. Okay, then pathfinding complete, callback. So in our constructor, we're going to be passing our starting node, our target node, our callback, and I think we can also pass the grid itself or the grid manager. I think I'm just going to pass the grid manager though. Okay, and that is our constructor. We need to have stored the starting node, we need to store the end node, and well, we also need access to the grid manager, so we're going to also keep that there. I'm just going to write it as grid. We have the callback, we have the started node. I think that's enough. So start node will be your start, and node will be your target, and then grid manager, or just grid, will be your grid manager. Awesome. Then your callback for basically this callback equals the callback you are passing. Okay, and that sets up the class, but it's not ready to use. Okay, to use this, we're going to have a method which is going to be called void find path. Okay, then we're going to need a list for a target path. Okay, and then we're going to basically do a list of node for find path actual. Let's return null for now. So find path, what's going to be doing? It's going to be saying that your target path will be returned from the find path actual. The find path actual is the method that is actually going to take the largest amount of time to finish. Okay, previously, if you have seen any of my other pathfinding videos, I was usually doing multi-threading in this case. So we will have a notify complete and so on and so on. However, there's a new method that I like to try and I want to do, which means we are not able to do multi-threading because we're going to be using a few things, recast. For example, that Unity doesn't allow to do outside of the main thread. Okay, so that means we can't really use multi-threading in this case, but it doesn't matter. It's still pretty fast And in my tests that I've done, it was really fast, so doesn't really matter, yeah, as I said. So then after this finished, keep in mind that it's always we're doing in a serialized fashion, so that means this method needs to first finish, and then you're going to call the callback. Okay, there's another way around it. Yeah, we need to pass the target path. So technically this will also work as well. Keep that in mind. So find path actual. Okay, we're going to do some basic, well, A star for the most part. Okay, which means you start with a found path, you start with an open set, and you have a hash set for just checking which are the closed nodes. So which basically are the nodes that you have already checked. Then you're going to add the starting node and the open set. Then while your open set dot count is greater than 0, while you have nodes to check, we're going to add this in a bit. Then we simply return the found path. Okay, so before we continue with this, we need a few variables inside our nodes, and that stuff is basically your heuristic cost, your G cost, which I never remember what it is, what the name is, and the F cost. So basically the F cost is your G cost and your heuristics cost. And one other thing that you're going to need is the parent node for this. Okay, I think we're good with this for now. We're not going to be checking if you're workable or not yet. We're going to do this on another part. And yeah, okay. So back to the Pathfinder on the open set. Let me check my notes. Then we can start having fun with our Pathfinders. Okay, so we first need, we first need our current node. Okay, and that will be always the first position of your open set. Then for each option you have on your open set, usually it's only one, but there's case that there'll be more than one. Okay, we're going to compare the F cost from your current node dot F cost, or the F cost is equals than the current node dot F cost, and the open set I dot heuristics cost is lower than the current node dot H cost. I think we need this to be inside its own bracket like this. Okay, okay, and if not current node equals the open set, so if it's not the same node, then the current node is now your open set I. Okay, after that we're going to be removing the open set, the current node, and we're going to be adding that onto its closed set. So if current node then equals the end node, you are there. So we're breaking, and we're going to say that we retrace the path in here. So now for each node, we're going to be getting the neighbors from a method that we still haven't added, but we're just going to write anyway. Get neighbors of the current node. Okay, let's create the method. we need a list of nodes for get neighbors from, okay, let's say return null for now. Okay, let's keep writing this. We also need a get distance actually. So let's find the distance. Get distance from position A, come on, and position B, and then we have distance x, which will be mathf.abs of position A dot x minus position B dot x, and then distance z will be mathf.abs position A dot z minus position B dot z. Okay, now if the case that distance x is higher than distance z, then the return value should be calculated based on the z, distance z plus 10. It's just creating a score, so don't worry if you don't understand this. It's not really that important, to be honest. It just calculates the score based on the distance, or well, it finds the distance between the two nodes. We add the 10 just so that we are using more values. It's actually how the A-star algorithm was, so I'd never really bothered learning or well getting into much into the details of this, to be honest, because why not? Because why? If you know how to use it, don't need to know how it works, I guess, just like your car. So if it's not a closed set, if the neighbor is not contained onto the closed set, which means we have not yet added, we're going to have to find the new movement cost to your neighbor, okay, which will be your current node g cost plus the get distance from the current node and the neighbor. Let's rename this to neighbor. Okay, then if the new movement cost to neighbor is lower than the neighbor c cost, or it's not contained into the open set, so that means we haven't checked it yet, then set up his costs. So we have neighbor.g cost equals new movement cost to neighbor. Neighbor, the heuristics cost is now the new distance from neighbor to end node, and the neighbor.parent node will be your current node. Okay, and if it's not contained inside, if it doesn't contain the neighbor now, the open set, we add the neighbor to the open set. Okay, so that's the basis of a star. We still need to write the retrace, and well, basically that's how you can go through the nodes without checking the new ones again and calculating the cost. In the get neighbors now, we're going to have to be checking for all the neighbors we need. Okay, we do have multiple floors, but for now I'm only going to be worried about one floor, the one we are currently in. Okay, as you understand, The Sims is a very simple game at some stuff, so there's no case that you could just climb a wall. So there's no case why we should be checking a node that is above us. If we want to go on a top floor or on a lower floor, we have entry points, and those entry points are, of course, the the stairs, and anything like that, anything else like that. Okay, so that means it makes our life somewhat easier because we only have to check on two axes. Okay, for z -1 and equals to 1. Okay, if x however is 0 and at the same time z is 0 as well, then just continue. Actually, we don't need this too. Just continue because it's the from node you are using. Otherwise, find me the x node, the new x node, which will be x plus the from dot x. Find me the y node, which is going to be hard-coded as the from y, and find me the z, which is going to be z plus from dot z. Then find me that node. Okay, get node from the grid. Let's see one thing. Yeah, okay. Actually, let's make a shortcut. Integer x, integer y, integer z, return grid dot get node x, y, z. Okay, get node x, y, z, and from that node we need to find the neighbor node, the new node. And then to do that, we're going to say node, new node equals get neighbor. It's not plural. And we kind of want to pass this node and the from node. Okay, so let's create the get neighbor node, get neighbor. And we have the, let me check, we have our search position and we also have our origin. Okay, then we're going to have a result which will start as null and then return the result. Now we can just say that in this case I'm just going to do result is the search position for now, okay, which is going to allow us to move anywhere inside the grid because we're not really doing any checks if it's walkable, if it's not, if there is a wall between the two nodes and so on. We're not doing anything yet. Okay, we're going to fix that later, maybe in the next part even. Okay, for now we just need this, and all that's left to do is basically have the retrace path, which all that's going to be doing will be to have a list of nodes. We're going to be saying retrace path node start, node end. Then you have your list of nodes, your path, then node current node. We start from the end node, and then while current node not equal to the start, we're going to be adding that onto our path. Okay, and then current node will now be the current node, parent node. And on that path, we're going to reverse that and return the path. And that's the retrace. Let's go and hook it up. Let's do one thing. Let's see one thing. However, yeah, okay. So found path equals retrace path from start node to target to current node. Awesome. So that's actually the entire path, and it's going, once this is finished, it's going to use the callback for that. So we have our Pathfinder. Let's create the Pathfinder master. Let's set it up a little bit, and then we're going to set up our game manager. Let's delete all of that. I'm going to say namespace. Okay. Now I'm going to make this under a singleton, so I can access it easily from anywhere I want. Although most likely I'm only going to be accessing it from the grid manager, or maybe we need to make a game manager. It doesn't matter. For now, it doesn't matter. We're going to create this. We're going to set them up correctly and as they should be later. So we're going to create a request Pathfinder. Okay. And we're going to be saying node start, node target, and we want to pass the Pathfinder dot Pathfinder callback. Okay, so for now I'm just going to be creating the Pathfinder now. We also need to pass the grid manager, so let's make this into a singleton as well. Come on. Okay, so we have new Pathfinder start target. The callback is a little bit of a problem, but we already have the callback and the grid manager singleton. Okay, I can now just say now find path, and it will do the path and it will do the callback all in a single frame, because we're only going to have one path finding. Okay. Now, let's minimize that. Let's create our game manager. New script. Let's call this game manager. Let's open that up. Let's add the namespace. Then, let's delete this. Then, before we actually do that, let's go on the grid object and let's say public node get current node. Okay, and how that's going to work, we're going to be saying return grid manager singleton get node transform.position. So I don't have to worry about storing the node each grid object is above. You can just automatically calculate it at that time. So we have our game manager, then void update. Then let's work some, well actually I just need a grid object, and first of all if grid object is null, return. Okay, then I need to know my current node, or actually need to know the previous node. Okay, and now I need to know also my current node. Okay, so how do we do that? We're going to first create array from camera.main.screenPointToArray from our input.mousePosition. Okay, and then if physics the raycast ray out raycast hit and 100, I think that's enough, and you can just say on all layers, we don't really have anything there. Okay, and if that's the case, then I need to find me the node we are currently in. So I'm going to say current node equals grid manager get singleton get node hit dot point. Okay, you can say if you want this to be clamped, but whatever. So if current node not equals null, and if current node not equals the previous node, then call for a pathfinder from the object, from the node position of the object to the current node, which is of course the current position. So I'm going to say previous node equals current node, then pathfinder master singleton request pathfind from grid object current node. Let's collapse this, let's break this a little bit. Grid object current node, the callback will be down here, void pathfinder callback. Later we're going to change this, we're going to add a little bit more logic and stuff like that. For now we don't have to worry that much. Pathfinder callback, and that's about it. And this will basically request you a new pathfinder. Now we kind of need to visualize the result, so I'm going to create a line renderer. I'm going to add a line renderer, and then we're going to create a list of positions. Or do we need a list? We could just say line renderer set positions. Actually, position count, yeah, to be p.count. Then for each node and in p, line renderer set position. We need this to be a for loop. For integer I p.count. Okay, and that will be I dot comma p, which is path node wall position. Let's add a little bit of an offset just so that it is above the ground. Okay, so this will basically create you a line of the entire path. Okay, so technically if we assign this and drop this into a game object, it will work. So let's test this out. Now let's see where we are. Save that. Let's create a new empty game. Actually we already have the game object. We need game manager. I'm simply going to assign one of these as a grid object. Don't even know which one it is. We also need to fix the camera though, so I'm going to say align with view, because we're going to be using this to use the camera obviously. And we also need to create the line renderer. Okay, let's change the color. That's good enough. And I'm going to also tick use world space. Okay, so assign that into line renderer and hit play, and we should get a pathfind something. Okay, we're missing, got one error. Yeah, we're missing the pathfinder master, so just add the pathfinder as well. It will be good to save because we might have something wrong inside our pathfinder and it could break everything. Let's see what this is. 63, what? Pathfinder 63. Neighbor, get neighbors in current node, what? Yeah, in this case, we are getting a node that it's null. But I have no idea why that is. I'm going to guess it's the first node. So let's put a pause into this. Okay, we're getting a few things off. First of all, let's check if we have this. And let's check what... No, I think that shouldn't matter. get neighbors. Yeah, we forgot to add over here the variables. So if the new node is not null, we need to add it into our result, which we do not have yet created. But add new node. That was the case. Okay, you can see the path that it takes. We're missing the starting node in this case. Okay, which is the starting node of the unit we are using. You can see this a little bit better. And I think if we go and remove the offset onto our callback, so let's see on the game manager, the first position I'm going to add +1. This will start as 0, and actually this will start +1, and this will start as 1, because line renderer dot set position 0 will be game object or grid object dot, I'm just going to use transform dot position instead of the wall position, and let's remove the offset. It should be above the ground at least. Okay, and yeah, no, I think that's okay. Okay, apart from a few errors, well, apart from having one more index that we need, that actually works, but we do get one more, which I'm guessing is this. I think if we skip that, it's going to shouldn't be. I think that will give us one more position, or that will make some positions not look correct. For example, still not wrong, but we are indeed off. Unless I'm doing something else wrong. Position. Yeah, okay, so you know what? You have your path. Let's remove that. Let's say 0. Okay, but the very first cannot add set position this will keep it first, so we need to add one more in below. Well, I thought that should do it. So maybe we can do this +1 and then p dot p line renderer set position 0 grid object transfer dot position. Yeah, now we're talking. Okay, so there's our Pathfinder. Of course, there's no real rules to it. We might have something wrong in our heuristics, because that doesn't seem that should have been the closest position to that. So as you can see, it kind of prefers diagonals, but the case for that is because we are just assigning a position to it. If we find a search position, we just assign it as a position. Okay, we're not really checking anything. So we should probably add a diagonal. Yeah, I think we should just add a diagonal penalty in this case. That will be over here. Somewhere over here at least. Okay, that's one way to do this. The other way will be, of course, to completely ignore diagonals, but I think they just work okay already, so no need to do that. I'm just going to check, I'm going to double check that we have everything correct in this. Let's rename this to move cost, so it's easier to read. Okay, so check cost, get distance, move cost, okay, heuristics, then neighbor add node, okay, parent node, current node, okay, node, neighbor, okay, then you retrace the path, then we have our f cost, if it's lower than the current node f cost, okay, and if it's the same f cost and the heuristics cost is lower than the current node average cost, that seems correct as well. Then in the get distance, position A, oh yeah, that's wrong. Position A from position B, that's it. Okay. Let's hit play. Now we should have a correct, well, probably. Yeah, now we have correct Pathfinder. Okay, so that's our Pathfinder, but of course it just moves from node to node. It doesn't really avoid the walls and do stuff like that. So let's see how we are on time. Yeah, okay, we are 40 minutes in. So we're going to treat the walls and the obstacle avoidance on the next part. As always, you know what to do. Like, subscribe, and if you like to see more stuff, more videos, more series, more of everything of this, then of course consider supporting me on Patreon so we can keep making all of these nice things we're making. I'll see you next time.